Welcome, students, and welcome to this Premium Explainer. Today we are focusing on one of the absolute most vital areas of modern software engineering, systems of systems architecture. If you've been following along, you know we've been building up to this. In a world governed by massively interconnected megasystems, architectural design is the absolute most crucial activity you will undertake when building a system of systems, or an SOS as we'll call it. We're going to dive deep into section 20.5 of our text today, and then we'll round the whole thing off with a rapid-fire master recap of the entire chapter.
Here's our roadmap for today's session. We'll start with the principles of SOS design, look at the problem with traditional frameworks, cover the 3 architectural patterns, do our master recap, and then finish up with an exam primer.
All right, Section 1, Principles of SOS Design. Let's get into it. Before we even think about building an architecture, we really need to understand the rules of the game. And what's absolutely fascinating about this quote from Mark Meyer, who is a real pioneer in systems engineering, is how it just completely flips traditional software development on its head. When you're building an SOS, Meyer gives us 2 golden principles. First, you have to design your systems to be useful even when they're incomplete. Think about it. If a massive network relies on every single tiny node functioning perfectly just to deliver any value at all, well, it's going to fail. It literally has to have stable intermediate forms. Second, be realistic about what you can actually control. You cannot try to over-control independent nodes. If you try to force rigid top-down control over external systems that you don't actually own, you are going to face resistance, massive delays, and ultimately failure.
Now, building directly on Meyer's work, Hilary Soletto provides us with a few more crucial guidelines. He suggests designing what he calls a node and web architecture. So what does that actually mean? Well, the nodes are the individual socio-technical systems, and whenever we say socio-technical, we just mean the blend of human behavior and technical infrastructure. So the hardware, the software, the people, and the policies all working together. The web, on the other hand, isn't just network cables. It's the formal and informal social communications connecting those nodes. You must also focus heavily on the interfaces between these nodes. But Soletto's absolute most critical rule? You must provide clear incentives for participation. Independent organizations are not just going to join your sauce out of the goodness of their hearts, right? You have to provide real financial, operational, or data-sharing benefits to convince them to plug in.
Moving on to Section 2, the problem with frameworks.
So a really common misconception for beginners is to think they can just use traditional enterprise frameworks for a system of systems. Things like the TOGAF architecture development method, which stands for the Open Group Architecture Framework. TOGAF, along with MODAF, which is the Ministry of Defense version, are designed to help architects build out business, data, application, and technology views. And look, they provide a really useful checklist of views to consider, but there is a glaring issue here when it comes to an SOS. The underlying assumption of these frameworks is fundamentally reductionist. By reductionist, I mean the belief that you can take a massive, complex problem, break it down into perfectly definable little pieces, and control all the moving parts.
And that leads us to a really crucial comparison. Traditional frameworks rely on this reductionist assumption of control. They assume there's a single, powerful governing authority that can just mandate changes, resolve all disputes, and maintain massive amounts of documentation overhead. But contrast that with the politically messy reality of an actual system of systems. In an SOS, control is totally distributed across different organizations. They might be in different countries, dealing with different laws, and holding completely different priorities. You simply cannot dictate a change to a system you do not own. It just doesn't work.
All right, Section 3, 3SOS architectural patterns.
Okay, students, please sit up and take careful notes here, because we are entering a major, crucial exam concept. Because traditional frameworks struggle so much, we have to rely on architectural patterns instead. Let's start with the first pattern, systems as data feeds. By definition, this is an architecture where you have one principal system that requires various types of data, and it actively queries other, completely independent systems to retrieve that data. The independent databases generally do not interact with one another at all. They literally just sit there and wait to be queried by the principal system.
A classic real-world example of this is a vehicle licensing system, like the MOT certificate system over in the UK. The government's principal licensing system needs to verify if a car is roadworthy and if it has insurance. But it doesn't actually store all this data itself. Instead, it acts as the principal system, pulling from separate, independent testing and insurance databases right at the moment you try to renew your license.
So how do we actually engineer this? Step 1, you absolutely must be able to identify entities uniquely across all the systems, like using a vehicle registration plate. Step 2, the principal system sends out the query. And step 3, pay close attention here because this is a very common pitfall. You must manage timeouts. If an independent external data feed goes completely offline, your principal system cannot just freeze up while waiting indefinitely for an answer. You have to engineer timeouts to ensure your system drops the connection and remains stable even when the external feeds fail.
Our second pattern is called systems in a container. Working from first principles, this means one primary system acts as a sort of virtual container or shell. It provides a set of common, foundational services, think things like single sign-on authentication or cloud storage. And it provides these services to approved constituent subsystems that are essentially placed inside the container. A great way to visualize this is to consider a digital learning environment, like iLearn. The container itself handles all the authentication, the storage, and the basic configuration. Attached to it are independent systems, maybe a science encyclopedia, MS Office 365, or Moodle. These subsystems don't have to worry at all about how users log in. They just plug right into the container's standard interfaces and utilize the shared services that are already provided. So the crucial takeaway here is understanding the trade-offs of this container pattern. The primary benefit is that it is absolutely excellent for incremental development. You can build the core container on day one and then slowly add approved systems over time as you need them. However, the drawbacks are pretty significant. You often have to write very specific, bespoke interfaces to force older legacy systems to talk to your new container. And critically, you have zero influence over the included external systems. Microsoft could push an update to Office 365 tomorrow that completely breaks your container's interface, and you have absolutely no power to stop them.
Finally, we reach our third pattern, trading systems. This is definitely the most complex of the three. A trading system is a completely decentralized network. There is no principal system pulling data, and there is no virtual container providing shared services. Instead, the constituent nodes negotiate and trade information directly with one another without any principal broker getting in the middle.
Which brings us to a really critical question for this pattern. What happens when there is literally zero governance? Think of high-speed algorithmic stock trading, where millions of shares are traded in a fraction of a millisecond. You have independent broker systems rapidly firing buy and sell orders directly to each other. Because there is absolutely no central authority checking everything, the main problem is that any system can break compatibility at any given moment. A node might update its application programming interface, its API, without any warning, instantly severing its ability to trade with the rest of the network. It's the Wild West.
Let's move to Section 4, Chapter 20, Master Recap. Okay, take a breath. We are now transitioning into a rapid-fire master recap to prep you thoroughly for your exams. First, let's reiterate the absolute fundamental definition. From a software engineering perspective, a system of systems is defined by having two or more independently managed elements. You really must remember Meyer's key characteristics here. Operational independence, meaning the subsystems are actually useful in their own right even if disconnected, and managerial independence, meaning they are governed by completely different people with different priorities.
Next up, we map the complexity. There are three types of complexity in an SOS. First, technical complexity, that's the actual software and hardware links. Second, managerial complexity, the day-to-day operational control. And third, governance complexity, the high-level laws, regulations, and overall policies. We classify systems based on this. Directed systems are owned by one single organization. Federated systems have independent owners but share a central steering committee. Coalitions, they have zero formal governance, just informal, voluntary collaboration.
And please, never forget why we can't just treat these massive networks like traditional, standalone software programs. Reductionism totally fails for complex systems. Remember, reductionism is the idea that you can break a problem down into its smallest parts to solve it. But in a system of systems, that fails because it assumes unified control and strict physical boundaries that just don't exist. In an SOS, boundaries shift constantly, and control is highly distributed. You cannot over-control independent nodes, you have to incentivize them.
And finally, Section 5, the exam primer. Let's lock this in.
All right, bring your focus to a razor's edge here. If you've been casually listening, grab your pen right now. Your examiners will absolutely test your ability to contrast the patterns we learned today. You must be able to explicitly contrast systems as data feeds against systems in a container. Just remember the core difference. In data feeds, a principal system actively pulls data from separate, distinct databases. But in a container architecture, the main system isn't just pulling data, it's providing shared core services, like a single sign-on, to the constituent systems resting inside it.
So here is your final checklist to memorize. 1. Contrast data feeds versus containers, just like we discussed. 2. Be prepared to explain exactly why enterprise frameworks like TOGAF struggle with SOS architectures. Remember, it's because they are reductionist and assume a level of top-down control that absolutely doesn't exist in reality. 3. Define technical, managerial, and governance complexity. Students, I want to take a moment to congratulate you. You've made it to the end of Chapter 20, and you have now officially mastered the foundational complexity of modern megasystems. You understand how the digital fabric of our modern world is actually woven together.
But our journey definitely doesn't end here. We've just spent all this time looking at massive, sprawling, politically messy networks. Next time, we are going to flip the script completely. We're diving headfirst into Chapter 21, Real-Time Software Engineering. I want you to think about this. Can you architect an embedded system that controls a pacemaker in a human heart or an aircraft engine in flight, where missing a processing deadline by a single microsecond could mean total, catastrophic system failure? It requires a completely different engineering mindset, and I honestly can't wait to share it with you. Until then, keep studying hard, and I'll see you in the next explainer.